Hello, this is Ms. Nichols, and this video is on magnetic induction. The essential question is, how can moving magnets create electricity? So first, a little definition. You'll be hearing the word induction. Induction means to create. Magnetic induction specifically occurs when we move any kind of conducting material perpendicular through a magnetic field. This is going to induce or create a potential difference, aka a voltage, across the length of that conductor. Incidentally, you can also do this by moving the magnetic field and keeping the conductor stationary because it doesn't matter which one is moving. Conceptually, I find a really useful analogy is to pretend that the magnetic field lines are infinitely long strands of spaghetti. And magnetic induction is going to occur anytime that conductor is chopping through the spaghetti. If you think about the wire that is drawn on the page, that red wire in the external field that's going in the x-axis, if you take that wire and you move it either in the x-axis like shown or in the y-axis, you are not going to induce any voltage in this wire because the spaghetti is not being chopped. We're just sort of sliding through the forest of spaghetti. However, if you take that wire and you move it in the z-axis, which is in and out of the page, I'm going to move it out of the page and you'll see what happens to those field lines. Okay, as it comes out, it cuts through those field lines, and that means that that kind of motion will be inducing voltage. The consequence of that voltage is that the electrons in the wire are pushed one way, the protons are left where they are, and we end up with a wire that functionally has a positive side and a negative side. The big law that governs this unit is known as Lenz's Law. Lenz's Law comes from conservation of energy. It basically says that energy in the universe is conserved, so if you're going to induce a voltage or create some electrical potential energy, it has to come from somewhere. In this case, the electrical potential energy is created from the kinetic energy of the moving wire or the magnet, right? We had to push it through that field somehow. Some force had to push or pull it through the field. One implication of Lenz's law that is kind of interesting is that whenever you are creating this voltage, whenever you're inducing voltage, the conductor is going to experience a force which feels like it is resisting the movement of the conductor. It kind of feels like friction. It's opposing the motion. This force is always in the opposite direction from the velocity. The reason is because the force must be in the opposite direction to create negative work, and that's that negative work that is pulling the kinetic motion energy and turning it into electrical potential energy. So this is the force that is actually doing that work. This diagram below shows a common example problem for this unit. It involves a circuit that has like one movable wire. It often is called, it's said it's on rail or something. It's like two rails up and down, and then there's like a conductor that's connecting them. So we have a complete circuit, but we can move one of the wires. If you move that wire to the right, the wire is going to experience a force to the left as it moves. So how do we figure out how much voltage is induced when that wire is moving relative to our magnetic field? The magnitude of the induced voltage, otherwise known as EMF, with that little symbol E, but that is actually a voltage, remember, depends on three variables about my experimental setup. The first is how strong the magnetic field is. So obviously a strong field has more spaghetti lines, and you are going to create more voltage when you move conductors through that. It's a linear relationship between V and EMF. The second relationship has to do with the length of the wire that is moving. The longer the wire, the more of those spaghettis it's going to be chopping, therefore the more voltage is going to be induced as well. That's another linear relationship. And the last variable is how fast that wire is moving. Obviously, the faster the wire is moving, the more spaghetti it's going to chop as well. That's another linear relationship. So the equation is pretty straightforward. EMF is equal to BLV, taking into account those three linear relationships. You can use the same old second right-hand rule we learned about earlier in this unit to figure out what direction those protons are basically pushed in the wire. And remember that it's actually the electrons that are moving, but the right-hand rule is going to give you force on a positive charge. So the way it would work is your fingers always point in the direction of the magnetic field line. So second right-hand rule is that straight one, right? We're not doing magnetic field of the source wire. It's force on an object from another field. So fingers point in the direction of the magnetic field. The thumb is going to now point on the direction of the wire that it's moving, the velocity of the wire. In that example I set up, I was pulling the wire out of the page towards me. So if you want to follow along, fingers to the right, thumb points out of your paper. And then the palm is going to tell you what direction would the protons be experiencing a force. If you've done it with your correct hand, you should discover that in this case, the protons are pushed upwards, which means functionally what we've created is a battery that has a voltage we can calculate using that equation above, and an orientation that we can figure out with the right-hand rule. So that moving wire could be used in a circuit as the voltage or as the battery. A second way of approaching this, if you actually have a complete circuit instead of just a single wire that is moving, is using a variable known as magnetic flux. Magnetic flux is represented by the Greek symbol phi, which is a circle with a line through it, sometimes with little tails on the top and the bottom. And phi, or flux, is defined as the amount of magnetic field that is passing through a surface of some kind. The number of spaghettis that are poking out through the circuit. In this class, we're usually going to use the surface that is defined by the shape of the circuit, but if you take more physics, there's other reasons to define different surfaces. Flux, the reason we use flux is because it's a lot more efficient to calculate the overall voltage or induced EMF in a system of wires than by trying to calculate the voltage for each wire and take into account the direction, etc. So flux takes into account overall the entire shape of the circuit. So for example, and I think I already mentioned this, but you can think of flux as the number of spaghetti pieces that are poking through the circuit. Flux is going to have a linear relationship with the strength of the magnetic field, and it's also going to have a linear relationship with the area of the circuit that is perpendicular to the field, because there'd be ways to make that area not perpendicular so none of the field went through it, and that's relevant as well. But A is specifically usually going to be the area of the circuit. So the equation to calculate flux is actually really simple. It's just B, the magnetic field strength, multiplied by the surface area of your circuit. One note about flux, it is a vector, which means that you need to calculate the magnitude of the flux, and you need to calculate the direction of the flux. When you use that equation, the units you're going to get are Tesla meter squared, because B is a Tesla and A is meter squared, and that is simplified to be a new unit called a Weber, or a WB. Quick example of calculating flux based on a experimental setup. If we have a square loop of wire that is 2 meters long on each side and it is fully inside a magnetic field of strength 5 Tesla, and you are asked to find the magnetic flux through the loop, that flux is just going to be B, which is 5, multiplied by the surface area, which for a square is length times height. So you get 5 times 2 times 2. The flux through this square would be 20 Webers into the page, because this is an in magnetic field. So we can use this new variable flux to, as I said earlier, efficiently calculate the induced voltage and current in a loop of wire. Since the flux measures how much magnetic field passes through the loop, anytime the total flux in the loop is changing, we're going to have a voltage induced. In other words, we have to have a change in the number of spaghettis poking out through that wire. Spaghetti has to be moving either in or out of the loop as a whole. If the amount of changing flux is more than 0 in any direction, then we will induce a potential difference across the loop of the wire, and we're going to have current flowing if there's a closed circuit. So in the example shown, as that loop moves out of the field, the flux changes through the loop, and that is going to create current flowing through that loop. If the loop of wire is just moving around inside the field, or for some reason the flux is not changing, like for example that, we're not going to induce any net voltage in this circuit, and therefore there would be no current. The thing that that allows you to calculate the magnitude of the induced voltage, or how much current eventually is going to be in my loop, is the rate of the flux changing. So how quickly are we chopping the spaghetti is really the thing that will tell you whether we get a lot of voltage or not a lot of voltage out of this situation. There's another equation on your equation sheet that says EMF equals negative change in flux due to a magnetic field divided by the time, and that tells me that it's a rate-related variable. The negative sign you can completely ignore. That has to do with the direction, but we're going to be using the right-hand rule to reference direction. So the bigger the change in magnetic field, the more voltage we're likely to induce, and the less time, the smaller amount of time it takes, again, that's going to create essentially a stronger amount of current. Once we have that voltage value, we can use that with good old Ohm's law, as long as we know the resistance of the wire in the loop, which it might have a resistor in it, or we can use resistivity. Then we can actually calculate how much current is in that loop as well, using I equals V over R. And we'd substitute in that E, the EMF, for the V value in that second equation. Let's take a look at a few common scenarios where the flux through a loop is changing. Remember that flux is the magnetic field strength multiplied by the area. You could have a situation then for flux to change, either the B or the A has to change. If the area the magnetic field is passing through is changing, we're going to have a change in flux. There's a few different ways we can set up our design to make this happen. The wire loop itself could be expanding or contracting. Sometimes they make wire loops out of slinkies, or they have that bar sliding along the rail. So this is like somehow I'm stretching my loop. That's obviously going to change the flex. Or I have that bar moving along the rails. That changes the size essentially of the loop, and that will also be a changing flux situation. Another situation could be the wire loop entering or leaving the field. I showed that one earlier, but obviously the flux through the loop changes when we enter or leave the field. Or you could have the wire loop actually rotating, and we'll look at examples of this in class, which is kind of cool. But as you rotate, it changes the surface area that is perpendicular to the loop. The other way is that you could be changing the strength of the magnetic field. So you could have an electromagnet that is somehow changing its strength, either because we're changing the amount of current through the wire, so the field it creates is changing, or because we're moving closer or further away from the electromagnet, or we could have a permanent magnet and our loop is moving closer to that magnet or further away, and we'll look at some of that example later. We can use Lenz's law for loops as well, with the rule of thumb that the new current in the loop is going to create an induced magnetic field inside the loop that resists or is opposite to the change in the flux through the loop. This is one of those slides where I would recommend you write this down, and then we're going to have to process this sentence quite a few times before you actually really internalize what is going on there. In general, if the flux through the loop is decreasing through any of the ways it could decrease, that means we're going to create a new magnetic field inside that loop in the same direction as the field that was already going through the loop. It's essentially adding back the flux that has disappeared from that loop. On the flip side, if the flux through your loop is increasing somehow, then my loop is going to induce or create a magnetic field in that space that is anti-parallel, or in the opposite direction from the original field. You can think of that as canceling out the additional flux that is occurring. So you have a situation, any of the situations, where, for example, the flux through your surface is decreasing in the in direction. The induced magnetic field will then be in to cancel out that decrease. If the change of flux through your loop is increasing in the in direction, my induced magnetic field will be out to cancel out the extra ins. On the flip side, if I had a field that was decreasing in the out direction, then we're going to induce another field in the out direction to basically balance us, bring us back to equilibrium. Or if we were increasing in the out direction, then we would have an induced field in to cancel out those extras. You can repeat this for left, right, up, and down fields depending on the setup of your flux situation. We're going to run through a few examples of this because I know that it's a little bit mind-bending. Let's just say we have this loop of wire in a field, and we know that the flux through it at that first instant in time shown is 20 Webers in the in direction. When that wire loop moves, we now calculate that the flux through the loop at its second position is 5 Webers in. In this case, we could calculate the EMF using the change in flux of 15 Webers divided by how much time it took, if we wanted to know the magnitude of E. And if we want to know the direction of the current in that loop, we need to figure out which way would this loop be creating or inducing field lines to cancel out that change. Since the field was getting weaker in the in direction, the induced field in the center of that loop is going to be more in the in direction in order to kind of counteract that change. So if you want to figure out the current, you're going to use this new induced field that was created as the wire was pulled out of the field, and you're going to take your fingers and imagine sticking them in the center of that loop, and then of your right hand, of course. And then you can grab the wire, and using the first right hand rule, you can figure out what direction is the current in that wire required to have created that induced field that was in. If you do it in this case, you're going to discover that no matter which wire you grab, you're basically creating a clockwise current, and that is what would happen in this scenario. We would actually induce a clockwise current in that loop. Here's another example with that sliding rail. That rail started at position 1, and then it has now been slid to position 2. The flux through the loop defined by position 1, let's just say we initially knew that was 20 Webers in. But at position 2, we now have more flux, bigger area. It's now 25 Webers in. Again, we could calculate the E using the change in flux per time. But the direction is a little bit trickier. You've got to think about what's happening. We are adding more flux in as we get bigger. Therefore, the induced field by Lenz's law has to cancel this out. So the induced field from the current in this wire that we're going to create must be out of the plane of the page to cancel out the extra ins that we got when we got bigger. So to figure out the direction of the current, imagine your fingers of your right hand coming out through the hole of that circuit and grab any part of the wire of the circuit with your right hand. And then your thumb is going to tell you what is the direction of the current through that wire at that moment. If you do this for any of those 4 wires, you're going to discover that the current continues in one contiguous loop. And in this case, it is in a counterclockwise direction around that circuit. One last example, we've got a permanent magnet here and on the left, and we've got a wire loop. It's hard to draw this, but it's sort of supposed to be going in and out of the page, perpendicular to the plane of the page, near a bar magnet. And I'm going to take that magnet and I'm actually going to move it closer or towards the loop. And the question is, what will be the direction of the induced current in the loop? There we go. Well, the magnetic flux is to the left because that's the way magnetic field lines for permanent magnets work, right? They're going into the south pole. So the flux is to the left. As the magnet moves to the right, though, the flux gets stronger. We're getting closer to that pole. We're actually getting more magnetic flux through that loop. That means that the induced field has to cancel out the increasing left field, and that means the induced field is going to be to the right. So I've chopped the loop off so you can sort of picture what's going on. In the center of the loop, take your fingers from your right hand and point them to the right. And then you can grab any wire, maybe grab that top wire or the bottom wire, and you should see that your thumb is going to indicate that current is going to come out of the top wire, or it's going to go in the bottom wire. So we essentially have current in the loop where we're coming out of the page on the top and then going back in and around and around and again. All right, we've reached the end of this video, so please take a few minutes to revisit the essential question, which is how can moving magnets create electricity? Thanks for watching.